So chapter 19, I know our roughest chapter yet, our third chapter on equilibria, and again, ionic equilibria and aqueous systems. So we're going to consider buffers, titrations, and solubility. So some really intense calculations here. We're going to have some pretty lengthy videos to post for this chapter. Like I always like to do as we start a chapter, I'd like to go through the review sheet and talk about the 5 things that are important from this chapter, and then we'll cover each one of them with a few sample problems. So for buffers, we have kind of qualitative and quantitative aspects of buffers. There really weren't a lot of qualitative aspects to buffers, but remember, it's important to think about what a buffer solution is, how it's prepared, what it does, and thinking about concepts of capacity and range. So review this sheet for those aspects. Also think about protonation states and how they relate to both pH, which is an environmental property, and pKa, which is a molecular property. So again, not a lot of sample problems that relate to this. So make sure to look back at the old quizzes because they're going to have some information that relates to this. Quantitative aspects of buffers, a little bit more important. And as we do buffer calculations, titration calculations, and as we do solubility calculations, I'm going to utilize a sheet that I put together here to kind of keep track of all of the pieces of information. We always want to think about who's in solution, if there's chemistry that's happening, if we've mixed things together, is there a volume change we need to consider to get to new concentrations? Once we have new concentrations, are there equilibria that we need to consider? And so do we need to make an ice table? And then from that, whatever parameter we need to calculate, do we need to think about doing some other properties? And so even though this is a buffers and titrations worksheet, so we're thinking about calculating pH, I'll still use this same sheet when we talk about solubility and relate it in that way. So that's buffers, qualitative and quantitative. Then we move on to titrations. And again, it's important to think about these from both a qualitative and a quantitative way. So qualitatively, being able to think about some definitions for titrations, thinking about the 3 kinds of titrations we do, strong, strong, and then the strong, weak combinations. Thinking about what addition of titrant will do, chemistry or contributing to changes in pH. Again, some sample problems that we did. There were really none that were specifically from the book, so we had some sample problems that we created to do as in-class problems. And so we have some qualitative things to think about. But more importantly, the qualitative parts build into quantitative aspects of titrations. And again, this is a huge calculation problem that we're going to be working through. So titrations, again, thinking about where the equivalence point is and calculating that, keeping in mind that equivalence point can be calculated as a volume to get there, or we can calculate the concentration of an unknown analyte at the equivalence point. We'll review each of these as they become applicable in the sample problems. But again, with titration problems, again, we're going to use these sheets and kind of keep a method going to think about who's in solution. Is there chemistry that happens? Have we mixed things so there's a volume change? Do we have equilibria to consider? And what at the end of the day is the parameter we're interested in? With titrations, with acid-base titrations, it tends to be pH. And then the last section to this chapter talks about solubility of ionic compounds. And so the idea is that we have some salt that does not completely dissolve and dissociate in solution. So we're going to have some of the ions that are in solution, but a lot of the salt is going to remain as the solid form. So we have a KSP, which stands for solubility product. So we can do equilibria with this. Again, thinking about how much of this will be in solution if we generate a saturated solution, so how much will be allowed to dissociate. Or thinking about other kinds of problems. What concentration might we need to raise our ions here to in order to force a precipitate to form? And so we'll look at lots of kinds of applications of equilibria with solubility in a few sample problems here. And as you can see, the length of sample problems is quite lengthy. So again, those are the 5 things that are important from this chapter: qualitative and quantitative aspects of buffers, qualitative and quantitative aspects of titrations, and then solubility of ionic compounds. Okay, so moving on now to our first sample problem. And this problem is actually going to use 3 of my sheets here because the problem is calculating pH for 3 different situations here. So calculating the effect of adding either acid or base to a buffer. Well, the first part is actually just calculating the pH of the buffer, and then part B is calculating the pH after you've added some base to it, sodium hydroxide, and then part C is calculating the pH after we've added some HCl to it. So I'm going to treat each of these as its own independent problem. We'll kind of transfer some of the relevant information to our worksheet here, and then we'll work through it. Remember, the first thing that we always want to do is think about who's in solution. And so for this, it says write down all species in solution, crossing out any ions that are spectator ions, considering the extent of dissociation. For example, if we have HCl, we really have H plus and Cl. There's no HCl in solution. We have to think about salt solubilities. So we'll revisit each of those as they become applicable. So for this problem, we have a buffer solution consisting of 0.5 molar acetic acid and 0.5 molar sodium acetate. So if we think about who's in solution, we have acetic acid and it's 0.50 molar. Now this here says to list the concentrations, volumes, and numbers of moles. Well, if they don't list volumes for us, we can't get the number of moles. So, and as we'll see with this problem, that's going to be okay. We just need to know the concentration that we have. The next thing is that we've got sodium acetate, which all sodium salts are soluble, so that dissociates into acetate ions. And again, we have the same concentration there. And we have sodium ions. Now, the concentration of sodium ions is 0.5 molar, but again, the sodium ions are a spectator ion, so we're going to cross those out. So that's all of the relevant information from our problem here. So I'm going to set this aside so we can work through this problem. Now the next question to ask is there chemistry that's happening? Well, as we'll see here for problems B and C, chemistry will happen when we add either a strong base or a strong acid, but we're just looking at the buffer solution before we start. So there's no chemistry that happens. So the next question to ask is there any volume change? Well, they never really gave us any volumes to begin with, which is fine for this problem. We don't need to know volumes in order to calculate the pH of a buffer solution. But there's no volumes given, so this is not a relevant question that we need to consider here. The next part is to consider an ice table. And remember, for an ice tables relate to equilibria. We have to think about what the reaction might be for this equilibria. So we've got acetic acid. The only other thing in solution is water. And so when acetic acid finds a water molecule, its only option right here in the presence of water is to give up a proton to water, which means we generate H3O plus, and we leave behind the conjugate base, CH3COO-. So if we consider an ice table here, we know that our initial concentration of acetic acid is 0.05 molar. Water, again, is not going to be part of our equilibrium expression. How this is a little bit different from, say, the problem that we dealt with in Chapter 18 is we actually have the conjugate base here, and that's 0.5 molar as well. So molarities, again, go in our ice tables. We don't need to worry about writing units here. Now, we're going to assume right now that there's no or not any significant contribution of H3O plus from any other source. So this sets up the kind of problem that we call a common ion problem. So this is the equilibria that would happen, and if we had 0.5 molar acetic acid, we'd make a certain amount of each of these. But because this reservoir, so to speak, has already been filled up by a common ion, less acetic acid is going to be allowed to dissociate. So we're going to go ahead and make our ice table here. So we're going to lose a little bit of this, gain a little bit of each of these, and again, these X's are going to be equal because for every one molecule of this that dissociates, we make one of these and one of these. So that's why these are all X's. Our coefficients here are all 1, so coefficients for our X's are all 1. 0.5 minus X, 0.5 plus X, and X. Now in this case, since I wrote an acid equilibrium, I want to use an acid equilibrium constant. And so that's going to be equal to H3O plus times CH3COO minus over CH3COOH. And we can look up, or in most cases, I'll give you values for equilibrium constants. In this case, the Ka for this is 1.8 times 10 to the minus fifth. We know, again, our concentrations here that we already put in as 0.5 molars. And we can go ahead and do what I'm going to refer to now as a pre-check. And if we go ahead and do a pre-check, that means we can put in our concentration of our acid and put it over Ka. And we need to make sure that this is greater than 400. And in this case, it is, okay, because our Ka is 1.8 times 10 to the minus fifth. So this value is going to be much greater than 400. And what this allows us to do is make sure that we can do our assumption. So being able to do our assumption here allows us to put in our values. So 1.8 times 10 to the minus fifth. H3O plus is going to be equal to X. Our conjugate base is equal to 0.5 plus X. 0.5 minus X. And again, if we make our assumption here, this is going to be equal to X times 0.5 over 0.5. Which means that our X, which is equal to our H3O plus concentration, is really equal to what our Ka was, 1.8 times 10 to the minus fifth. If we take the negative log of this value, because remember this is our concentration of H3O plus, as we defined X as, so negative log of this will give us pH, and that's equal to 4.74. So again, this is equal to H3O plus. Negative log of that is equal to 4.74. Now actually, at this point in working through our sample problems and working through the chapter, we hadn't yet learned about the Henderson-Hasselbalch equation, but I'm actually going to show you how that would work with this problem here. Henderson-Hasselbalch equation says pH equals pKa plus the log of the conjugate base concentration over that of our weak acid. So in this case, pH is going to be equal to negative log of 1.8 times 10 to the minus fifth plus the log of 0.5 over 0.5. So that's the log of 1, and the log of 1 is going to be equal to 0, which means that pH is just going to be equal to the negative log of 1.8 times 10 to the minus fifth, which is what we did up here. So that's also going to show us that the pH is equal to 4.74.